we want to calculate the concentration of H3O in a buffer solution prepared by mixing the salt with the weak acid HF. Well, the first thing, if we're mixing solutions together, the concentration goes down, and the concentration goes down by the equation M1V1 equals M2V2. So we need to determine the new concentrations of the salt and the acid. So for NaF first, the initial concentration is 0.1. The volume is 200 mils. I want to solve for the new concentration, and V2, the new volume, is 300. I'm mixing 200 mils of NaF with 100 mils of HF. So my new concentration for the salt, 0.067 molar. I'm going to do the same thing for the acid. M1V1 equals M2V2. Initial concentration is 0.05. Initial volume is 100 mils. Solve for M2. V2, final volume, 300. So the new concentration for the acid, 0.017 molar. Now that I have the concentrations, I can solve for the concentration of H3O plus in this buffer solution. My equation is HF plus water forms H3O plus F minus. Concentration of HF is 0.017. H3O is 0. And F minus is 0.067. The change is just X and minus X. We set that equal to Ka. Ka is 6.7 times 10 to the negative fourth, and that would be equal to products divided by reactants. Now technically I'm not supposed to use the shortcut here because my Ka value is 10 to the negative fourth, but in order to save time I'm going to use the shortcut and solve for X, which is the concentration of hydronium, and that comes out to a value of 1.7 times 10 to the negative fourth molar. Titrations are procedures in which a solution of known concentration is added to a solution of unknown concentration until the reaction between the two is complete. Let's suppose, for example, we have a standard solution of sodium hydroxide, so I know the concentration of sodium hydroxide, and a solution of hydrochloric acid of unknown concentration. How do you know the point at which the reaction is complete? Well, we're going to use organic compounds that are called indicators that change color between the acid form and the base form. So we're going to use acid-base indicators to determine when the end point occurs in a reaction. For example, bromethymol blue is an acid-base indicator that's a weak acid, and a Ka value of 1 times 10 to the negative seventh. So I have a Ka expression. I'm going to rearrange that Ka expression to solve for hydronium. Hydronium would be equal to Ka times the acid form over the base form or the ionized form. Let's look at this problem here. I want to know the pH range over which the color change occurs for bromethymol blue. The yellow color is seen when the acid form is 6.3 times more concentrated than the ionized form. So let's start there, the yellow color. I want to solve for pH. So let's solve for H3O. And I rearranged the Ka expression earlier. Ka has a value of 1 times 10 to the negative 7. And the yellow color can be seen when the acid form is 6.3 times more than the ionized form. So HIN would be 6.3 compared to the ionized form, which has a value of 1. So my H3O concentration would be 6.3 times 10 to the negative 7th for the yellow color, and that corresponds to a pH, when I take the negative log, of 6.2. Bromethymol blue changes from yellow to blue. We're going to solve for pH there as well, so we'll solve for H3O. Ka is 1 times 10 to the negative 7. Now the blue color can be seen when the ionized form is 4 times more than the acid form. So we're going to give the acid form a value of 1 and the base form a value of 4. So solving for H3O here, we get 2.5 times 10 to the negative 8th molar, which corresponds to a pH, when I take the negative log, of 7.6. So the pH range over which this color change occurs is from 6.2 to 7.6. The yellow color is seen at a pH of 6.2 or below, and the blue color is seen at a pH of 7.6 or above. The end point is where this color change occurs. The equivalence point is a calculation. Ideally, the end point, what you see, should correspond to the equivalence point, what you calculate.